Dobra, momencik, tylko tutaj wystartuję.
Close it for a minute.
Okay, I think we are ready to start. So, hello and welcome to the next Warsaw University Astronomical Observatory seminar series. And today we are only Zoom only because of some clash with some other parties happening in Warsaw. So people are not available physically, but I see there is interest, and also this talk is going to be recorded. So I hope many people will benefit from the very interesting topic we're going to hear about today from Mariusz Slonina, Sybilla Technologies, about monitoring of space debris, challenges, problems, and Polish specialization. So Mariusz is an astronomer, is a professional astronomer. He did his master in astronomy at the University, Copernicus University in Toruń, and he wrote in his biography that he is a space safety expert working in Sybilla Technologies. He has been involved in a multitude of European Space Agency and commercial projects within the space surveillance and tracking domain, focused on ground-based utilization, sensor network operations and management, astronomical algorithms, data processing and analysis, leading to space traffic control services. Recently responsible for deployment, on-site integration and commissioning of the 12 telescopes of the Polish Space Agency Optical network dedicated to tracking of satellites and space debris. Mariusz, please, the floor is yours.
All right. So thanks a lot for inviting me to such a a university talk. I'm always happy to talk about space debris and things we are going and things we are doing in this domain in Poland, because as I will try to convince you that we have a huge astronomical heritage, and we can make use of it also in commercial services and providing satellite operators with the data they need. I will just switch my cam off. It will be easier a little bit for me whenever it's. Not stop video, stop cam, or all right. Anyway, all right. So my talk is divided into three sections. The first section, or the first two sections are more public outreach, but I wanted to give you some sort of a global view of what's happening in space and why and how we are relying on what's happening on space, on how we rely on space or safe space operations. And the last part will be about what we have to deal and how we deal with observations, and especially on the example of the newly launched Polish Space Agency Optical network, which is dedicated to monitoring space debris and satellites. So long story short, let me ask you a question. Have you ever wondered how much we rely on satellite data? I did such an experiment, a thought experiment, and I selected 3 applications that I use almost every day on my smartphone. Most of us are smartphone users, so I'm not different here. And for me, the 3 applications I use the most is the fitness tracking application, which tracks my health status, which helps me improve my health, my racing results and things like that. The second application is obviously weather forecast, how to dress when I go outside, whether to take an umbrella with me or not, because I don't want to end up being wet in the middle of my trip. And the third application is a typical map application. So it takes me from point A to point B using the shortest available path. It shows me that. and I can drive, safely, also avoiding some traffic jams and other obstacles. These applications, they have in common that they use location services or navigational services, satellite navigation, using different types of satellite GPS constellations, like GPS, American GPS, like Galileo system, like for example, even Chinese Beidou system. And but they are and they are used in my daily life to such an extent I can show my friends, for example, that I will be delayed because the bus is delayed, and I knew it, and I know it using and I know it by navigational services included within the application. On the other hand, when I'm, for example, in a new place, when I've traveled to somewhere and I want to eat something in a good restaurant, then I use location services and to find restaurants nearby. Or I can also share my current location to my friends. So that's a typical usage of satellite services on my phone. In my case, in your case, it might be a little bit different, but I assume that at least weather forecast and maps you use every day, or almost every day. It's a typical usage of satellite navigation. But satellite services are not only tied to our smartphones; they are used more widely in several applications. The first such of an example I can give is the example of agriculture, where we're using satellite services. Farmers can monitor watering levels, crop levels, how it's going with the food production and things like that. And especially they can monitor whether we have some whether they have or they will have issues with crops, maybe some sort of natural disaster. Some insects will destroy the crops. And speaking of issues, satellites are excellent in long-term monitoring of things which are happening on Earth. For example, climate change. We've collected using satellite imaginary a vast amount of data, which is used right now for monitoring climate change. It's a huge topic right now. Monitoring natural disasters like hurricanes approaching Europe coast or American coast or whatever country. Earthquakes, like recent example of earthquakes in Morocco. This is a radar map from the Copernicus system, which helped rescue teams to approach injured people and to secure them and to rescue them on time. On the other hand, satellites can or allows us to monitor also the activity of human on Earth. For example, the methane flows from Polish mines, and having that or having capability of monitoring such cases can help also securing crews which are miners and before any sort of disaster can happen, right? We can monitor the outflow of the gas and then we can have alerts. We can provide alerts to miners that something is bad happening. Also, what satellites shows us is the growth of cities on the Earth, like in this image of Warsaw, and the light pollution, which is also dangerous not only for birds, not for other animals, but also for humans. This map shows perfectly the light pollution of Poland, and there are just few patches where you can expect really dark night. There are like in Biebrza. And all of this is showing us what's happening on Earth, how the Earth is changed under the human influence, and how we can react or we can secure our activities. Last but not least, satellites can provide internet connection to places where there is no LTE or there is no other broadband connection. This is a Starlink terminal. Also, very popular and very active Starlink constellation, providing internet access in places where there is no other source of the internet. And going further with the internet access, there are services on our smartphones which will help to rescue us in case of any emergencies using satellite data, so that you don't have to have an LTE or broadband connection on your phone to call emergency teams to rescue you, wherever you are, whether you are on the sea or in the mountains. That leads me to a conclusion that satellites are essential to our daily lives, and we take it for granted. A few years back, there was a study of the European Commission that showed that 405 mobile application or used satellite data to providing services. People were subscribed to those applications, so there were business models behind, and the business model, the businesses behind those applications, they were paying significant amount of money to satellite operators that they have data back just to ensure that their business will survive. And 405 applications or 405 applications were based on that. Nowadays, I will risk a theory that 100% of applications is using or almost 100% of applications is using satellite data, and at least my life depends on that, and many of my friends also using satellite data. So this is so securing the operations in space is essential for securing our daily lives on Earth. But there's one more example how precious is the Earth's orbit for us right now, and it's the International Space Station. You probably heard that there will be a Polish astronaut going to International Space Station next year. But apart from that, the International Space Station, being in orbit for the past 25 or so years, it's a significant laboratory providing, for example, new drugs for cancer. So new materials. So all of the things, all of the research and development happening on the International Space Station goes back to Earth, and people are using it, even if we don't know the particular example. I can't speak of many examples of what happened on International Space Station. For example, in terms of medicine, because I am happy not to have health issues, but someone might survive because of the research conducted on the International Space Station, and that's why we should treat Earth's orbit as a natural resource, the same as clean air or clean water, and we have to take care of it here and now, not in 50 or 100 years from now, but we have to take care of it right now, because if we don't do it, and I will show you why, if we don't do it right now, we will lose this precious resource in 50 years, not 100, not 150 years. It's just 50 years. So it's a situation we have to solve right now. And this is what space safety is all about. It's about securing space assets in a form of active payloads, active satellites from any from space debris, which are we as humans, we are responsible for that, but also securing, for example, power grids from space weather issues, like a high velocity particles coming into Earth's atmosphere, and which can destroy a power grid. And there were examples, for example, in Canada in late 80s, 1980s, where the power grid was down because of the space weather, and there were pretty northern lights that time, but it was disastrous for power grids. There are also observations of near-Earth objects, which I will not cover here because I'm not focused in my domain with the near Earth objects, but this is also a significant significant part of the space safety domain, and because simply speaking, asteroids can destroy life on Earth, and we have to also monitor sky for such objects, and it's really difficult because they are dim objects. And we don't have a full sky coverage, monitoring skies just for them. So space safety is all about securing space assets for the life on Earth, and this is the message I would like to pass to you. And I want that you will somehow memorize at least one such a thing. That's why because we use satellites each and every day, and this is so crucial for our daily lives that we have to take care of it here and now. And what are the challenges? First of all, if we want to use satellite services each and every day, then we have to send satellites into space. And the first issue is that we are sending a lot of satellites as a humanity. Right now, it's at least 50 satellites per week. Last week, there was a Transporter 9 launch with Polish satellite on board, and it was 90, so almost 100 satellites just in one launch. This year will probably surpass 3,000 satellites sent into orbit within a year. And this number increased rapidly, especially in the last 2 years. It's an activity of SpaceX, mostly sending Starlink constellation, but also other commercial companies. The amount of active payloads or satellites into orbit is growing rapidly, but within that area, within that growth, especially one orbit is becoming very crowded. It's an orbit between 400 to 600 kilometers. It's the most precious part of the low Earth orbit, and it's in an orbit where International Space Station orbits. There is a Chinese space station. There are Starlink constellation. There are a lot of Earth observation satellites like Copernicus Sentinel constellation, and most of them are commercial. And then there are some of the defense satellite or military satellites, and there are obviously civil and amateur satellites like amateur CubeSats, which we send into space each and every week right now. And after the launch, once we put the active payload into space, there are some space debris or leftovers which are left within the orbit. Some of them can return like lower stages of Falcon 9 rockets, but most of them travels the orbit at high velocities for some time until they re-entry. This leads us to an issue of space traffic control and avoiding collisions in space. And there were collisions in space, and they will be happening more often in near future. One of the example is of Iridium and Cosmos satellites collided in 2009, and the missed distance, so the distance they should pass each other was computed to be around 0.5 kilometers. So it's for Earth's operations, for example, if you want to pass something within the range of 500 meters, you are surely to do it safely. In orbit, because of the uncertainties and high velocities, this was not that sure, and the satellites collided with each other and then polluted orbits around 800-kilometer altitude. And because of the atmospheric drag, the space debris, they are polluting 500-kilometer altitude. As I told you, this is the most precious part of the low Earth orbit. There were collision avoidance maneuver, or there are collision avoidance maneuvers like avoiding collision between ESA-L satellite and Starlink 44. This was the case where Starlink 44 satellite was the issue for the ESA-Ls, because it was crossing the original orbit of the European satellite. but the European satellite has engines, had engines on board, and it was able to correct the orbit and do the collision avoidance maneuver, which was costly because it shortens because of the amount of fuel needed for that maneuver. It shortened the life of the satellite, and it was satellite which was providing wind observations. Also, Polish example, Bright PL Heveliusz satellite, which missed the rocket body of Pegasus by only 4 meters. And I can tell you that this was really hot Christmas for Polish Space Agency 2 years ago. Collision avoidance will happen, and conjunction events will happen more often in the near future. Right now, at least at 500-kilometer orbit, we have around 30 per year. With the growing number of satellites, the number of conjunction events will obviously grow, and this is what this is what space traffic control will be emerging or will emerge for that. Such services will be required for safe operations. But space debris are not only produced within the collisions of satellites; they can also be produced during breakups events, which can be natural breakups. That is, the satellite explodes by itself, or it's hit by a small particle or other space debris, or they can be a result of a anti-satellite weapon used in low Earth orbit, and all of the major players, including USA, China, Russia, India, they did that in recent years, and it's highly irresponsible behavior. Because it pollutes during the atmospheric drag, it pollutes all of the orbits around Earth, and even might make them unusable for some time. Also, we are polluting the orbit as astronauts. For example, 1 month ago there was an example where astronauts lost the bag full of tools. Right, and it's now traveling 8 kilometers per second around. So that's such an example of that. But what is the point of space debris? Why they are so dangerous, and why we have to take care of them? Let me show you an example of CubeScout S1. It's a CubeSat of a small size, 12 by 5 by 5 centimeters. Its mass is 400 grams, so it's half of a kilo of sugar. And it travels with velocity 8 kilometers per second, which you can simply compute that this is comparable to a fully loaded truck traveling at 90 kilometers per hour. So a single, half of a sugar, it has amount of half of a kilo of a sugar has a amount of impact energy is comparable to an impact with a fully loaded truck at our roads. And because of this, because of the size and the mass and the velocity in the orbit, tracking and avoiding collisions with such debris, it's really difficult, and it takes significant amount of observations and time. To this point, that for example, each of the satellite has its own pizza box or a protected region. For International Space Station, it's defined as a region with the International Space Station being in the center of such a box, and the box dimensions are 50 by 50 by 4 kilometers in total. So the station itself is 100 meters wide in size, but the protected region is 50 kilometers wide, and anything which travels within this or hits this or it's possibly hits this pizza box, this protected region, raises an alarm that may lead to evacuation of astronauts from the International Space Station. And I recommend a reading of Scott Kelly Endurance book, in which during his 1-year mission he explains or shows what this evacuation scenario looks like in real time, and they didn't know whether the space debris would hit the station or not. They were not sure because of the uncertainties we have in orbit. And collision avoidance maneuvers are costly. They may happen even dozens of time a year, and and it happens also for other satellites, especially those who have, especially those which have engines on board, because CubeSat they don't have. So it's if they will crash, they will crash. Simply as that. But the International Space Station can be also hit with smaller objects, not only huge objects like this lucky strike of Canadarm arm. So just a tiny 1 millimeter in size or even less object hit the International Space Station. If there were an astronaut working with this Canadarm arm, he might not survive, to be honest, such a hit. Also, the windows of International Space Station, they are constantly hit by microspace debris, and the International Space Station it's covered with a shielding, some sort of shielding, multi-layer shielding, to be so that it protects for hitting with small debris, but it cannot be protected. But the space station itself cannot be protected, for example, with collision with such a CubeSat like CubeScout S1. Also, satellites are prone to collisions with space debris. The example of recently launched in 2016. So, Sentinel-1A satellite, or an Earth observation satellite, just after the launch, it was hit by 1 millimeter in size object, and it caused a drop because the solar panels were hit. It caused the drop of the solar energy provided by the panel, and also reduced a little bit the lifetime of the satellite. What's the scale of the problem? Nowadays, we track more than 35,000 objects or space debris in orbit. They are in size of more than 10 centimeters. So from 10 centimeters up to few meters. The biggest satellites, or for example, LAN or NVSat-1, which is a huge space debris on a 700-kilometer orbit. In addition to those 35,000 space debris, we have almost 10,000 active satellites, 9,000 something, mostly commercial satellites providing internet, and so they have to be tracked. The smaller the object size, there will be the more the objects will be in the orbit, and the estimates right now shows that around 1 million of objects is expected from 1 centimeter to 10 centimeter in size. They are really hard to be observed, even with radar techniques. They are not certainly possible to be observed using the optical telescopes. Right now, we have this limit of 8-9 centimeters right now. I will show you an example of such observations. And smaller objects like less than 1 centimeter in size, up 1 millimeter in size, we estimate that there's more than 130 million. And then we have this space debris dust, which we cannot simply avoid, and you can throw any sort of a number here. It's huge. But what is the real problem with not treating the problem of space debris? Because we've produced a lot of space debris, we track some, and we send more satellites into space. So it's likely that we will have more space debris in coming years, and that may lead to a problem which we called a Kessler syndrome, which is kind of a chain reaction in orbit, that one debris hits the other one, then we have more debris, then those debris hits other debris or other satellites, and the chain reaction will make an Earth orbit basically unusable for the time being. And previously, a few years back, the the simulations show that this may happen with the business as usual, as we call it. So we don't take any action with space debris mitigation. That it will happen around 2100 something. Right now, there are even some studies that it may started on lower orbit, especially because it's especially crowded. So we have to take action not to make the situation worse. So the Kessler syndrome basically grounds us on the Earth's ground, because we will not be able to send anything useful to space, because it will be immediately hit by a space debris after the launch, and that's why the European Space Agency came into an idea of a kind of a sustainable satellite life cycle from the design phase to operation, through operation, in orbit servicings and re-entry, so that we can avoid this Kessler syndrome, especially in lower orbit. And this is happening right now. They call it right now a zero debris initiative. Many countries already, or many companies already signed it. And this will be a thing in the near future, to design the lives and to manage the life cycle of a satellite, so that the Earth's orbit become more sustainable. For example, one of the advice for new launch, or one of the emerging laws for newly launched satellites, tells that the satellite has to be deorbited after the maximum of 25 years in orbit. The higher the altitude in orbit, the deorbiting phase will be more difficult. But it has to be done, because without it, we'll end up with Kessler syndrome in lower orbit very quickly. All right, so how do we manage that problem right now, or with the tools we have? And it is a wide topic, and I will focus just only on the optical part of the ground segment, because this is what we do every day. There are just before it, there are some missions, for example, like a rubbish truck, like clear space mission, which will target some larger space debris, and will show in 2 years' time, 2 or 3 years' time, whether we are able to get some larger debris back into Earth's atmosphere. But this is the future. Right now, we are using a ground segment in a form of also astronomical observatories to track space debris and to provide the data for the satellite operators. And it involves not only a astronomical observatories, typical astronomical observatories, but also it connects radar systems and laser systems, like the one in Borowiec near Poznań. And these different techniques, these different observational techniques, they allow for different observations strategies, and to detect different objects depending on the altitude in orbit. But what's the difference from the astronomical observations is the timing. First of all, we have to have a global network of sensors, so everywhere, or almost everywhere in the world, that has to operate 24/7 without interruption, because to monitor space debris, we cannot afford just having one observation of a space debris, or one observation of a satellite, and that's it. We have to do it in a constant manner using different telescopes, because there are different environment conditions, day and night, things like that. Also, different altitudes, and some of the altitudes cannot be reached by using optical telescopes. Some altitudes cannot be reached by radars or lasers. We have this requirement of delivering process data within 48 hours from the tasking request. I mean, we get the schedule from, for example, data center or satellite operator. and we have to provide the data as quickly as possible. The typical time for European assets, it's 48 hours. It will be shortened in probably 1 or 2 years to 24 hours. So that makes our software and our processing chain more stressed to do such operations. As I mentioned, there are different types of techniques, like radars are best for tracking LEO objects, but they lack some spatial resolution. Laser stations are best for tracking LEO and lower MEO. LEO low Earth orbit spread, the highest altitude is around 2,000 kilometers. The MEO region goes from 2,000 kilometers up to geostationary at 36,000 kilometers. So the MEO region can be also, at least the lower part of the MEO region can be covered by laser operations, laser observations, and they do it very precisely because they precisely know where to point, and they know the distance to a satellite. So, for example, combining optical observations and laser observations in scenario like star and chase can also help in tracking new space debris or newly detected space debris or a satellite in trouble. We have a very strict rules for providing the optical data. We have to keep at least 3.6 arcsecond RMS of after the plate solving, after the plate solve, and this is the upper limit. What's possible for European assets. After that, the orbit determination process, basically you can trash it, and the data will be unusable for any of the data analysis, any orbit determination process. We have to use precise timing using GPS satellites, which are in orbit. And the time tagging precision has to be around 1 millisecond. It's for observations to have this overview. Typical optical observations of a satellite, it's 1 up to 4 seconds, and we have to have the time tagging up to 1 millisecond. Because without it, we cannot easily, or we cannot precisely correlate with the satellite ephemeris. We cannot correlate the satellite ephemeris properly, and within the 1 millisecond, it's even a few hundred meters difference. And if you recall this missed distance between Cosmos and Iridium satellites, it's the distance within which you can either destroy your satellite or secure it. We, as data providers, optical data providers, we simply cannot, or it's really difficult to send raw data. That's why we are keeping the raw data on servers on the sensor side for some time, usually 1 or 2 weeks, and then the data is deleted. What we send is the processed data only in form of a so-called tracking data message, which is an XML or ASCII format containing raw measurements, right ascension, declination, and magnitude of a satellite or a space debris within the period of time which was tasked. And this is a compressed data, and this is the data which is required by satellite operators to be provided. The nice thing about optical ground segment for space safety is that we can use astronomical equipment as it is. Either it is an older telescope or a newly built telescope. It can be used as is, and this is the data which was provided by Campus Observatory Gashing Observatory in 2017, as far as I remember. On the right side, you see the Cosmos 2426 satellite. It is a GLONASS constellation, which was tracked by a 10 micron mount, I believe so, a 0.5 aperture, 0.5 meter aperture, and a CCD camera. And on the left side, you see simple observed minus computed chart showing the precision of the plate solving for this particular object. And for space safety operations, such an equipment was excellent at that time, because the measurements were less than 0.5 arcsec. And the pixel size, as far as I remember, was 1 arcsec per pixel, so it is a sub-pixel accuracy, and it was one of the key points of our project, Astrometry24.net, which we did for European Space Agency. That time, one of the examples that the software was capable, and software and hardware were capable of doing space safety ready observations practically without any particular algorithms or equipment upgrades. Yeah, and summarizing that, how the flow from the ground segment to end users securing satellites and orbit, or deciding whether the maneuvers will be taken, looks like is that on the left side we have the sensor network, whether they are optical, radar, or laser stations. Then we deliver data to national operating centers. The one in Poland is located in Warsaw, in Polish Space Agency. Then the data is delivered almost automatically to European operating centers, like the one operated by European Union Space Surveillance and Tracking Consortium, and then they provide services like collision avoidance service, like re-entry service, like fragmentation service to end users, so that, for example, satellite operators can take action using those data, whether they will schedule a collision avoidance maneuver, or they cannot do anything right now. But what is the Polish heritage here, and what is the Polish specialization or expertise in that? First of all, we have a vast network of optical sensors around the world, and it's a significant input to a European consortium network. Those Polish flags are, I must tell you, that they are not all shown here, or there are multiple even sensors within very close locations, like in Chile or South Africa or Australia. Right now, in one observatory in Australia, we have 6-7 sensors, and the optical network from civil engineering, which is covering re-entries. Yeah, so it's 8, I believe, as far as I remember correctly. Just in one observatory in Chile, we have 5 telescopes for our Polish Space Agency telescopes. So one telescope is from the University of Zielona Góra. In South African observatory, there are already 6 or 8 telescopes dedicated to space safety. So the locations are pretty much occupied, but we have new deployments coming up also in Asia, in South Korea, and in Spain. Also, there are plenty of telescopes on Tenerife, continental or North America, and also there will be new deployment in Hawaii next year. So we have a lot of them, and this is not only network which we as a company operate or provide, but there are. I mean, we have as a country, we have our combined network is really huge. There are other companies like Six Roads, which has more or less a network providing more data on MEOs and some of the space safety operations. There are telescopes of University of Adam Mickiewicz as well, and CBK from Poznań. Also, not only Polish telescopes are used. We are the operator of telescopes such as Pirate Coast, visible in the picture. They are the Open University telescopes, which we operate, and they do educational. They do educational observation. They do scientific observation, and they do as well space safety operations in the time windows which don't collide with scientific operations. And for example, these are satellite observations just after the sunset or just before the sunrise, in which astronomical observations might be difficult to conduct, but for satellite observations, they are perfect conditions, because also the satellite is lightened up by the sun. As I mentioned, we have laser station. It's a very good resource, a very good asset, Polish asset as well. And we also did scenarios like Star and Chase and other projects and ESA projects that we show that we are able to pass observations from optical telescope to a laser station, and the geographical spread was a few hundred kilometers from one telescope to another one, and we were able to track a satellite using or testing such an approach. Summarizing that, as a country, we did more than 30 ESA projects regarding space safety operations, from the low TRLs that are feasibility studies up to TRL 7, 8, which is a commercialized products available on the market. We are an active member, and we actively participate in European Union Space Surveillance and Tracking Consortium from 2018. And as a country, as different institutions, scientific institutions and companies, we provide a reliable data within the limits, or even surpassing the normal or typical limits of required for space safety operations. Our data is used to secure more than 400 European satellites, which are mostly Galileo and Copernicus satellites, and some of the project results were commercialized, like ABOT. It's a software which we developed at Sybilla Technologies to control and automate observations. Also, our data processing chain called Astrometry24.net, which was designed for satellite data for data processing of satellite imaginary, but it can be also used for typical astronomical observations. And the space safety in Poland became one of the pillars of Polish space sector strategy. It's a significant input to what Poland can give and can be a leader in, because we are trying to be leaders in rocket launchers. It will take time. We are not able to build a huge satellite right now on our own. Smaller satellites, as the Intuition 1 recently launched, is an example of that. We are capable of doing smaller satellites like CubeSats. But in space safety domain, we are considered as leaders, and I can tell you that with the recent launch of the Polish optical network, there are countries in Europe which are really jealous of what the newly launched network of telescopes can achieve. And I will show you some slides about the Polish optical network, which was launched recently for Polish Space Agency. The network consists of already 12 new telescopes which were deployed and commissioned this year. It's frankly speaking, it's 2 days. It's 2 days before the commissioning phase ends, and the telescopes goes to a fully normal operations, starting from the 1st of December. The telescopes are located in 3 locations: the Australia Siding Spring Observatory, the South African Observatory and Deep Sky Chile telescope farm. Each of the location consists of the four telescopes, and they can observe either together a single part of the sky, or they can do observations of different objects at the same time. There will be 8 more such of telescopes, which within the next few months. The 4 of them will be installed in Utah, and the last 4 will be installed in Hawaii. So after that, the Polish Space Agency will have covered almost all typical orbital regions. So they will be able to provide data on almost all satellites in orbit. And they are dedicated, and all of the telescopes, they are fully dedicated to space safety operations. They don't have filter wheels, so just a simple imaginary, but they will track satellites and space debris, and they do it already on a regular basis. Speaking of hardware, what's installed, the telescope is based on the L350 mount. The ESA optical tube is a 300 millimeter aperture, 1.5. I forgot the word. Never mind. They have integrated focuser, and the camera which is attached to the optics is QHY411. It is an SCMOS camera which is connected to a control computer using fiber optics. It can provide 10 plus frames per second, a full frame. In crop, it is even a higher frame rate when we crop the data. The full frame is 14 by 10K, and it can be as large as 60 megabytes in size. So we don't do typical such observations because it's it takes a significant amount of space, and it's not needed for typical tracking scenarios. It may be needed for survey scenarios when this high pixel density that can help in surveying the sky and detecting new objects. It has a custom-made GPS receiver, which allowed us to reach 1 millisecond of time tagging precision, and which was required for high frame camera. And the field of view is combined is almost 190 degrees combined. I mean, the 4 telescopes, because they can observe combined part of the sky. It's Abbott controlled. It is the nice thing is that we are reaching almost real-time data processing using Astrometry24.net with the aperture and PSF type of photometry using Gaia DR2 G band. We do also object correlation and tracker generation on site, so that we send TDMs, tracking data message, back to the client immediately after the observation, and or almost immediately after the observation, which may take up to 2 or 3 hours, depending on the scheduling and how many objects have been scheduled. The data flow ranges anything from 250 gigabytes to 1 terabyte of data, and it's because of the 2 terabytes disks. We have to erase the data each and every night from the sensor. It is kept on the server side for 1 or 2 weeks, but after that, the raw data is simply erased, and the TDMs are what's left after the measurements. Here you have some images showing the numbers of the real data processing. As it was August 2022, so we are around 1 arcsec with this almost 2 arcsec pixel, 2 arcsec per pixel. The pixel scale, we are reaching sub-pixel accuracy, even for the razor sharp focused system like here you have on Polsat 3C and Polsat 3D. We can even reach lower than 1 arcsec, and they are really good results for such a system, for such wide aperture and high and huge frames. The data delivery comes anything from 20 minutes to 3 hours. It's far below the limits which are for space safety operations. But what's more important is that during using the automation system, we ensure that whenever there is a weather, where have I whenever there is weather, then we observe, and there is no operator needed for that. This is how we achieve such numbers here for those system for this system, especially the object count per hour, which is for the whole system combined, 12 telescopes combined. So some of them will have weather issues, some of them will have a day-night limitation issue, but still it's more than 35 objects at once per hour observed, and this can be only higher with upcoming scheduling updates will provide for the system. But what can be really observed from the observer point of view with this system? This is the smallest thing we've ever observed using Polish optical telescope. It's a CubeScout S1, the one I've shown you previously. It's a 1 second exposure of a satellite at a 600-kilometer orbit. It was done in binning 1 by 1. It's a crop of a full frame image, and zooming in, it's like that. It's just not a single pixel for such an object, but there are a bunch of pixels, and you can measure them. This is real object reflecting light. It was really tough observations. They were done in fully manual because they required very specific lighting conditions to see such an object. But right now, that kind of system can reach such objects. And if you asked me a few years back whether it will be possible or not, I will just tell you this is not possible and will not be possible. But now this system provides you such capabilities. Last but not least, going to an end, we've also tracked re-entry scenarios, and we helped the European Space Agency to track the re-entry of their ESA-L satellite. It was the lowest possible altitude for our optical equipment, or optical equipment of University of Zielona Góra, because it was the Rotus telescope or Panoptis 4, tracking L's at 260 kilometers altitude. 1 or 2 days before it re-entered, it was sent back to Earth's atmosphere to burn out and to end its life. The image on the right side, it's just reflecting light or passing light of the satellite through the clouds. To be honest, we would be able to even track it at 160 kilometers, but it was 4 or 5 degree altitude already, and it was reaching the limits of the telescope farm itself. This observation was taken at around 9 or 10 degrees above the horizon. And we also, for the space safety operations, not only re-entry, and not only space debris, not only re-entering satellites, but also launching satellites. Where are they? Maybe they should. So you see newly launched Transporter 9. They are these tracks in a survey, because the observation is did in a survey mode, and it's also the lower part of the image is 8 degrees above horizon. The upper part is 10 degrees, so 10 degrees above horizon, and it's really difficult also for optical observations because the orbit is sun-synchronous orbit of this when the satellite were launched into, and it's the orbit which almost prevents optical observations of a satellites, but we were able just before the just after the sunset to get these observations right. So this is also the capability of a typical astronomical equipment. This one particular located in Australia, and yeah. And I think that's it from my side. If you have any questions, I will be happy to answer it. Sorry I took so much time, and I just covered just the basics of the topic behind. So yeah, I'll be happy to talk to talk more about it. I think you are muted. I don't hear anything.
One, two, three.
Oh, yes, now I hear. Yeah.
Okay, sorry. So I was clapping and saying that this image is so mesmerizing that I can't stop looking at it. Thank you, Mariusz. Are there any questions? I have one, of course. So the CubeSat you showed, like an image before. Yeah, this one. So this is 1 second exposure. What is the magnitude roughly of this object here?
I have no idea, to be honest. I can't remember. I will have to check it with the team, but that's a good question, obviously.
Yeah, exactly. And it actually, I can continue with that as a follow-up question. You showed that there is way more debris and satellites also, which are faint. It's like in logarithmic scale.
Mm-hmm.
So how do you think this field should grow and develop in order to tackle this problem that there is so many of the faint ones, and you probably need bigger telescopes? And so this is my question: how do you think larger telescopes, which are already there, maybe could be useful for this?
I think we can certainly make use of them. I didn't talk about 1 meter telescope, which we are be operating in the next few weeks, because I didn't receive any imaginary from that, and I don't want to speak about some ideas of what's behind. I just want to have this real image. But certainly, this is also that they are also in our interest to see faint objects. There are also techniques which are more or less offline in terms of data processing, that you can stack multiple images and to have this signal to noise ratio much better, especially in survey mode. For tracking scenarios, you precisely know what object you track in advance, because this is the tracking scenario. So you have to point the telescope in the right direction and time. But for survey modes, combining multiple frames and larger apertures may have a difference. And we are, as I told, in a few weeks we will have access to 1 meter telescope, and we are also eager to test any other larger telescope for such scenarios. Yeah.
Right, and the 1 meter, where is it going to be located?
In Chile, Deep Sky, Chile.
Deep Sky, Chile. Okay, that's a good location for this kind of stuff. But probably you need more than one telescope to trace these. And also, you showed that the further orbit, I guess these satellites are also getting fainter and also slower, right? So maybe they're easier to track with larger telescopes.
Yes. The rule of thumb is that for LEO lower orbit is 1 second exposure at maximum. It's typically 0.3 second, 0.5 second, but 1 second is maximum because of the underlying star field and issues with plate solving after that, because the strikes will be too long. Then for MEO, you have 2 second exposures, which work best, also especially for GPS satellites. And for geostationary orbit, it's 4 second exposure, and that's enough. And they are basically not moving much within the underlying star field, and we can treat it as stars. To be honest, we treat all of these observations as a stellar kind of observations. One difficulty is that within the tracking observations, you have stellar field as tracks, and the satellite is a point, but they don't differ in data processing much from the astronomical data processing. The correlation has to be performed using a little bit of trickery, some sort of transformations between celestial and terrestrial objects and the orbital ephemeris for satellite, but it's all doable. It's not a hidden magic book after all.
Right. So, and how many objects you observe with the entire network every night, given the luminosity cutoff and so on? How many objects you track?
I will not answer properly for this question. It's from 400. I can give a number for the Poland network because I operate or I supervise this network. Typically, we have around 160 out of 400 objects per month. And there are more on observations. It's not like we have a single observation of that object, but there are continuous observations of such objects. And not all of the objects from the list are available for those observatories because of the geometry in orbit. And with the observatories on the north hemisphere later in next year, it will be the coverage will be much better. And for our network, I mean the Panoptes Solaris network, because Solaris telescopes known from the Solaris project, they are also used for tracking MEOs, for tracking GPS and geostationary objects. They have narrow field of view, so they are perfect for that. And they are not perfect for LEOs because simply you just see not enough stars to compare for the plate solving. But for the MEOs and GEOs, they are perfect with what they have currently, and it's really old equipment. So I think it's hundreds of objects, different objects, but it depends on to be honest, it depends on the satellite or on the scheduling. We don't do it on our own. Like we don't select the list of objects to observe. We are tasked by Polish Space Agency and European consortium and other partners to follow particular objects. But the network itself should be able to, for example, to have on its own, to have a full geostationary scan each night. So all of the objects orbiting at this level, at this orbit should be observed. But it's right now we are filled with requests from other parties.
Okay, thank you very much, Mariusz. I don't see any more questions, so let's stop here and I'll clap on behalf of everyone. Thank you, and let's stay in touch. Thanks. And thank you all for joining. See you next week.
Thanks a lot. Have a good afternoon. Bye.